Hello and welcome. Today, we're diving into the fascinating and complex world of predicting when and where a satellite will fall back to Earth. It's a critical task for space operations and safety, involving a deep understanding of orbital mechanics and atmospheric science. The main reason satellites deorbit is atmospheric drag. Even though the atmosphere is incredibly thin at orbital altitudes, it still creates friction, slowly reducing a satellite's speed and altitude. This is especially true for satellites in low Earth orbit, or LEO, which is typically below 2,000 kilometers. So, what influences how quickly a satellite decays and re-enters? Several key factors are at play. First, and most significantly, is atmospheric density. This is highly variable, largely due to solar activity. When the sun is active, with events like solar flares, Earth's upper atmosphere heats up and expands. This increased density at higher altitudes means more drag on satellites, making them deorbit faster. Conversely, during low solar activity, the atmosphere contracts, reducing drag and extending a satellite's life. Predicting solar activity, especially the 11-year solar cycle, is a major challenge. Second, the satellite's own characteristics matter. We talk about its ballistic coefficient, basically, how much atmospheric drag affects it. This depends on its mass, cross-sectional area, and drag coefficient. A satellite with a large, light structure, like big solar panels on a small body, will experience more drag than a dense, compact one. Even the shape and whether it's tumbling can change the drag. The materials a satellite is made of also determine how it burns up during re-entry. Some tough materials, like titanium, can actually survive and reach the ground. Third, its orbital parameters are crucial. Satellites in lower orbits face much higher drag and decay faster. The inclination of the orbit also tells us the latitudes over which it might re-enter. Now, how do experts actually predict these events? It's a multi-step process. It starts with tracking and observation. Ground-based radar and telescopes, along with space surveillance systems, constantly track satellites and space debris to get their current orbital data. Then, scientists use sophisticated atmospheric models. These models estimate atmospheric density at various altitudes, incorporating solar activity forecasts. Finally, specialized software takes the satellite's current orbit, its ballistic coefficient, and the atmospheric model predictions to project its trajectory forward in time. This estimates the decay rate and predicts the re-entry window. But it's not easy. There are significant challenges. As mentioned, atmospheric variability due to unpredictable solar activity is a big one. For older satellites or debris, we might not know their exact shape or material makeup, leading to uncertainties. If a satellite breaks up during re-entry, predicting where individual fragments will land becomes incredibly complex. Plus, precise long-term predictions demand a lot of computing power. Despite these challenges, accurate deorbit prediction is more critical than ever with the growing number of satellites. It's essential for space situational awareness, knowing what's happening up there. It helps in risk assessment, allowing for warnings if needed, though the risk to individuals is extremely low. It also aids in debris mitigation by understanding natural decay and planning for controlled re-entries. Research is constantly pushing forward to improve atmospheric models, refine how we estimate satellite characteristics remotely, and even use machine learning for better accuracy. International collaboration in sharing data and research is also vital. The goal is always to narrow down those re-entry uncertainty windows, which can currently span from hours to days. It's a continuous effort to keep our skies and ground safer.